Hoi! In the previous video we constructed the Kleisli category for a monad, at least on fake paper. Now let's see if we can also do it in Agda. So remember that the idea of the Kleisli category was that it's a category of effectful functions. And the point was that we needed exactly these laws for a monad in order to prove that the resulting thing really was a category. Right. So here I started the construction. So given a monad M, I'm trying to construct a category. And I'm saying that my objects in this category is going to be the same as the objects in the underlying category the monad is on. So this is just the objects, first I have to load the file, the objects of C. But I'm saying that here the morphisms from X to Y are the morphisms in C from X to M of Y. So that's act MY in Agda speak. Right. Okay, and then I have to construct an identity, which then should be a morphism from X to M of X, but that's exactly what my return natural transformation does. So that makes sense. And then here I need to do a composition. And we said that I should start by doing F, and then after that I should do the F map of M of G, and after that I should join things together like that, and that gets me where I want to be. So that's the data, but now we also have to prove that we satisfy associativity and the two identity axioms, right? So I'm going to use the solver for this, and I'm going to do one of these in detail and then speed up the other ones a little bit. So I think this is one of the most interesting ones. So I'm going to do this one. So I've already copied down what I need to prove and converted it into the syntactic form, right? So this is what we need. Okay, so let's see what we have. Well, we have something which already looks pretty decent, right? There's no brackets in the wrong way or anything like this. So let's see what we can do. Well, we want to get all the way down to just an F. So we are spotting opportunities for simplification using these axioms, right? And we can't see anything immediately, but we see that here, if we could just get this return to touch with this join, then this axiom here is going to make them disappear into a dark hole and just become the identity, right? So it looks like a good strategy to try to make these two things touch. And how do we make them touch? Well, we could use the naturality of return to commute it past things that are of the form F map of something, right? So I'm claiming that, first of all, I want to focus on this area. All right, and focusing is for free. Solvcat can do that for us. Okay, and then inside this area, I would like to use the naturality of return. So that means that I go from F map after return to a return after F map of something. And in this case, this something is actually, let's see if I can find it. This one is particularly simple, right? So here is return before an F map, and here I just have F before return. So if I do that, I think this just becomes F. Okay, so that at least type checks. And then here, okay, let's worry about proving it later, because now here I can move my focus to focus on the radical reaction I want. It should be this one, and moving the focus is for free. That's solvcat can do that for me. And then here I'm claiming that inside my focus this should just become the identity, and then I'm claiming that solvcat can deal with identities for me. So I just have to fill in these two holes. Let's start with this one. It's not going to be for free, but we can look at the reduced thing we need to do. Okay, so here we see now that we need first proof that this is equal to this, and the proof that this is equal to this. So the first one is simple, and here we actually have to do some work, so we use RQ. Okay, and we need this, but we said that this was naturality of return. So let's try that. Oh, with respect to f. Okay, that doesn't quite look right. I think we need a sim of that. Yeah, so that works. And here, once again, let's look at the reduced goal. It's something and then simple. And this something here is the equality of this and this. So that was the return join of m. Again, maybe we need a sim of that. No, is it not return join? Oh, it's RQ of something, sorry, and then it's return join of m. Okay, so that proved it. So we see that we needed exactly one of these axioms for this one. Okay, let's do the other ones as well. Okay, so that wasn't too bad, although, and it was greatly helped by having solvcat, I would say. I'm not just tooting my own horn here. I think that otherwise this is almost unmanageable. So we see that we follow the same pattern where we start, we do a solvcat to reposition the focus, then we do a real thing, so here was join join, then we do a solvcat to reposition the focus, do a real thing, which here was the naturality of join, and then we do a solvcat. So we interleave these two steps. Move focus, do something, move focus, do something, etc. Right. Okay, so see that for associativity, we need a join join. For identity left, we needed map return join. And for identity right, we needed return join. So we used each one of the axioms for each one of these. And conversely, you can check that if you assume that this is a category, then you will have exactly these axioms. So in a sense, this is really where they are coming from. Right. And we also use naturality of both join and return in this construction. Right. So that's also needed. Okay, I hope that's illuminating. It's explaining why monads are the way they are in some sense, because we really want this to be a category.